For this geometry task, we're going to be talking about tiles. So imagine the scenario where you're in the kitchen of your house and you need to put down a tile floor. And you're looking at a company that sells the tiles, and you find out that the cheapest way to get the flooring is to get tiles that are all the same shape. Okay? So what shapes can we get? Are all shapes possible? Can we get triangles? Can we get squares? Can we get pentagons? Can we get hexagons and all kinds of sided figures? What are the limitations? Okay, so for an example, let's look at this tile floor that's in front of us, and we see 1, 2, 3, 4, 5, 6 sided figures. So these are hexagons that are all placed together on this floor. And the reason we can use hexagons is because they stick together without any spaces in between, right? We don't want any spaces in our floor. We don't want to be falling through. So there's a mathematical term for this before we get started, and it's called tessellation. That's when the sides of all these shapes exactly match with each other, and you can look at any vertex on these hexagons and they all look identical. No matter where you are on the floor, you can pick a vertex and it looks just the same as all the other ones. Okay? So let's explore our regular polygons and see which ones will tessellate. We'll start with our three-sided regular polygons. We'll have our triangles here. Okay? So I've created a triangle and duplicated it 6 times and spun them around, rotated them around the center point, and it looks like they do tessellate because they meet in the middle, all of their segments align, and there's no space in between. And we can extend this out in all directions. So we can determine that equilateral triangles do tessellate. Squares, our regular 4-sided polygon, also tessellate. I duplicated this square into 4 other congruent squares and rotated them about this point, and they do tessellate. All their sides line up and there's no space in between. Now what about regular pentagons? Okay, this one looks a little weird. So created this, duplicated it 4 times, and we have a little overlap here. So I can drag this out, and you can see that no matter which way I try to put this in here, it's just not going to fit. It's just going to stay there. If I leave this on the starting point, there's nowhere where I can move this congruently and make it fit in the spot. Okay, so pentagons aren't working for us. What about hexagons? Well, as we saw in the first example, hexagons do tessellate. I can put them together, no problem. I can even take my original and just slide it right in here, and I can make all the hexagons I wanted and slide them into all of these open spots around the edges. Okay, hexagons work. Now, can we just keep going up forever and just keep getting ones that work? Well, if we look at septagons, this one looks kind of weird, okay? So I made 3, and they overlap right here. If we keep them congruent, where one side lines up, the other side is never going to line up. If we rotate it, we're going to throw off our balance. So septagons aren't going to work for us. Now if we continue on to look at the octagons, they're not really going to work either, are they? So we've created 3 congruent octagons and try to put them together, and there's no way we can align this side and get the adjacent side to go into this spot. Honestly, it looks like a right angle here, so we could fit a square in there, but we're definitely not going to get an octagon to go in there. So, what's the rule? When can we tessellate regular polygons, and when can we not tessellate them? Take a minute and think about it. You can open GeoGebra yourself and play around with it and see if you can come up with any ideas. Now, let's go back to our equilateral triangles. Those did tessellate. Let's think about why this might work. Okay, what do we notice about this figure? Well, they all meet in this point, and if we go out on these little spokes here, since they're equilateral, we know these are all the same length. That reminds me of radius or radii of a circle. Let's see if they line up on a circle. We can come over here to the circle tool, make B7 our center, drag it out to an edge, one of the edge points. Wow, okay, so all of our vertexes line up on this circle. That's kind of cool. Well, the square works, so let's try it on the square. So we'll do the center point and then drag it out on the radius. Okay, so they are radiuses. All of these points where they tessellate and the segments are radiuses that come from this vertex in the middle. Alright? Now, this one didn't work. The pentagon didn't work. Let's remove the one that doesn't fit. We'll put it down here for now. And let's see what happens if we make a circle out of this point, I3 right here, and drag it out to one of the vertexes. Alright. So it does cross here and here with our two radii that we do have, and the edges of these other pentagons. Okay? And then if we try to put this one in, well, it crosses on one segment and the radius of the other, but we have this overlap, so that kind of ruins our tessellation. So with this little slice of the circle we have left over, this angle just isn't big enough to fit this pentagon in here. So maybe it has to do with angles. Let's try the hexagon, just to make sure our circle thing is really working, okay? We'll use the center vertex right here, drag it out on the radius. Yeah, all our radiuses fall on this circle. Cool. Okay? So maybe it has something to do with the angle left over when we have our circle. Something about angles. Something about angles. Well, equilateral triangles have 60-degree angles. We can actually take our measuring tool and prove that right here, okay? 60.2. I didn't drag these exact precisely, but all of these are 60-degree interior angles. What's 60 times 6? You can do that in a calculator. 60 times 6 is 360 degrees. Well, that's kind of cool, because that's how many degrees are in this circle right here. Alright. Well, does that trend continue? Let's see. For our square, 90 degrees on the inside, 90, 90, 90. So we have 4 90s. How much is 4 90s? 90 times 4 is 360. Okay, so that fills up our square. Now, do we remember how much our interior angles of a pentagon are? Let's take our measurement tool again, and we can find out. We'll measure this angle right here to the middle and then down this side. 106.3. Let's redo that. We have this to the middle. 108.3. Okay, so that's about 108 degrees. So 108 5 times makes our 540 degrees for the pentagon. That makes sense. Okay, 108 degrees. Well, we tried to fit 3 here. Well, 4. Well, 108 times 2 is going to give us 216. But if we add on a third one, our third one would give us 324. And if we add on a fourth one, we're going to get at 432. So it skips right over 360. So 108 will not divide 360. Interesting. Okay? So our hexagons, let's look at that. We come over here. Our hexagon angles are going to be, I believe, 120. Should be close, 120.7. Okay? So, theoretically, in a perfect world, this is 120 degrees. 120 times 3, we have 3 hexagons, is going to give us 360 again. So, 120 does divide into 360. So I think what we can conclude from this exercise is that if the interior angles of the polygon will add up eventually into 360, then they will tessellate. So our only options for regular polygons are equilateral triangles, squares, and hexagons. Okay? That's what we have proven with our interior angle conjecture for this activity.